Threat identified. Small asteroid bearing plus 102 degrees by minus 3.4 degrees.
Target acquisition mode.
Target is orbiting asteroid 65803. Diameter of main asteroid is 780 meters. Target has a diameter of 160 meters. Distance of separation is 1.4 kilometers.
Mission control. Threat identified and confirmed. Permission to engage target.
Permission granted. Fire at will.
Engaging with Dart Impactor.
Dart deployed.
Activate Draco.
Draco activated and locked on target. Collision course confirmed. Ion propulsion system at full power. Velocity approaching 6,600 meters per second. Impact in 5, 4, 3, 2, 1. Impact force 3.3 meganewtons. Asteroid deflected.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. The previous scenario is no longer science fiction. The DART impactor will strike a small asteroid, orbiting a larger one, far away from Earth. This mission is called the Double Asteroid Redirection Test. Let's take a look at Kinetic Impactors. Please don't forget to like and subscribe, and help us out on Patreon if you can. We appreciate you. DART is a real kinetic impactor spacecraft, ready to launch into space later this year. The target is a binary asteroid called Didymus. The two asteroids orbit each other every 12 hours, and are tidally locked. Didymus was discovered in 1996 by Joe Montani of Spacewatch. Binary asteroids are not uncommon. These occur when two asteroids come close enough to start orbiting each other. This causes both asteroids to orbit about the center of mass between the two. Both asteroids making up Didymus have a combined mass of almost 528 billion kilograms. Can I say teragrams? No. Fine. Billion kilograms. These asteroids have a density of 1.7 grams per cubic centimeter. Earth has a density of about 5.5 grams per cubic centimeter, and ice has a density of 0.92 grams per cubic centimeter. If we look at what we know about the asteroids, we can estimate their individual masses. These asteroids have been visualized with radar from Arecibo, with a wavelength of 12.6 centimeters, and confirmed by the Goldstone Radio Observatory at 3.5 centimeters. This is an actual image, with each pixel being 15 meters across. Here you can see an equatorial bulge. It is not uncommon for these to develop when an asteroid is composed of smaller pieces that can shift when it's spinning. These asteroids have a similar albedo, at about 0.15 optical. If you saw the lesson on the James Webb Space Telescope, you will recognize this as the same albedo as Mars. They are reflecting back about 15% of the light directed at them. These asteroids having a similar albedo means they should have similar compositions. The diameters are 160 meters and 780 meters. That gives us a radius of 80 meters and 390 meters, respectively. We know that the volume of a sphere is calculated with the formula 4/3 pi r cubed. These are not exact spheres, but close enough to give us an estimate. Pulling our numbers into the equation gives us 2.1 million and 248.5 million cubic meters, respectively. This means the smaller asteroid is less than 1% the volume of the larger one. If density is the same for these two, that would give the smaller one a mass of about 4.5 billion kilograms, of the total 528 billion. Didymus has a perihelion of a little more than 1 astronomical unit, and an aphelion, or farthest distance from the Sun, of 2.28 AU. This takes it from just past the orbit of the Earth to well outside the orbit of Mars. The original mission plan was to orbit a probe around the asteroids before impact. This probe would have been built by the European Space Agency and been called the Asteroid Impact Monitoring Mission, or AIM. The combined mission would have been called IDA, for asteroid impact and deflection assessment. The Europeans would have launched AIM in October of 2020. It would have targeted the Didymos binary asteroid system. The smaller one is sometimes called Didymoon, by the way. AIM was equipped with a high-resolution imaging system and would have gone into orbit around the target asteroid, imaging the surface in high resolution and sending the images back to Earth by laser communication. It would also have high-resolution radar to see below the surface and an infrared imaging system. The infrared imager would collect any infrared light reflected or emitted by the surface of the asteroid. This can help us understand the composition. AIM would also have deployed a small lander. The lander would have come down to the surface fairly gently and would have emitted a radar signal that could be recorded on the other side, a sort of radar CT scan, so we could know the interior of the asteroid. AIM would have then deployed 2 CubeSats. These would have taken up station near the asteroid to help record the impact. But this didn't happen. The AIM monitoring mission was canceled by the Europeans. The Americans went ahead with their part of the experiment, and DART is scheduled to launch on a Falcon 9 Block 5 from Vandenberg Space Force Base on the 24th of November of 2021. Rockets launched directly south from Vandenberg to go into a polar orbit. The DART impactor, sent by the Americans, will come in at full speed, 6,600 meters per second. At a mass of 500 kilograms, it will indeed hit with a force of 3.3 million newtons. But AIM won't be there to see it. The DART does indeed have a Draco camera system. Draco stands for Didymos Reconnaissance and Asteroid Camera for Optical Navigation. Draco will help us determine the impact site as DART comes in. And DART has now been equipped with 2 CubeSats of its own. These are 6-unit CubeSats with a mass of 14 kilograms, built by the Italian Space Agency and called Licia Cube. Licia stands for Light Italian CubeSat for Imaging Asteroids, and is probably pronounced Licia. 10 days before DART impacts, these CubeSats will be deployed at a velocity of 1.1 meters per second by a spring-loaded mechanism. And with the help of onboard propulsion, these 2 cameras will be 3 minutes behind DART to capture scientific data and imaging of the impact results and send it back to Earth. This type of research is critical to human survival. At some point, the Earth, or an off-world colony, will be threatened by an asteroid impact. If we have our Starship threat detection system working, we should detect it in time to take action and avoid catastrophe. The DART mission is vital to understanding these impacts, and is a clear example of NASA at its best. Thanks for listening. Please don't forget we have Academy-themed gear in the Academy store, and stay safe at Astra Pro Terra.